Okay. So turn in whatever you got to turn in here.
Did you read that there's no more concept theory?
Yeah, I got so excited.
We got to gain a day.
Okay, so how do these term symbols go? I think, for me, I don't know about what you guys are going to think, but this is where everything finally comes together, all this stuff, and you finally see an application for it, right? Well, I don't even need to write that. I'll just write the big L, and subscript J, right? So do you see these term symbols? You have to figure out each energy is going to have a term symbol. Some might be degenerate, but you can just use them to describe the states. And here's how we write our term symbols, right? We had this in class already, I think, right? We talked about what big L is. If L is 0, the letter is supposed to be a S, that kind of thing, right? If it's 1, it's supposed to be a P. Okay, so we're going to start with an electron configuration for a many electron atom. We're just making it simple at first, helium. But look at what's coming up. We're going to be able to describe, this doesn't work, describe lines and transitions. So, and it works for everything. Compare that to where we came from. Do you remember where we came from? We started out the period, so we started out the chapter. Let's find it here. Where is it? We're in chapter 13. What the heck happened? Chapter 13. Oh, I'm already there. Ah! Thanks, Padawan. See, this is where we started out. We started out, do you remember this? With some high school teachers who found some simple mathematical relationships to say why there's lines in the hydrogen spectrum. Didn't really mean anything, right? It works for hydrogen, just a mathematical trick. Well, now we're going to have a process, an actual method, an actual procedure to identify these states, okay? Taking into account everything we've been talking about. So let's apply it, see how it works. Okay. So derive the atomic term symbols for the helium atom, and here's its electronic configuration. Does that look like it's in the ground state?
No.
No. That's okay. We're going to derive the term symbols for that. Okay. And why is there more than one? Spin, orbit, coupling. Jeez. Okay. Well, you'll get used to the words in a little bit. It's all foreign language, I know. Okay. Let's start here. We remember and I would stick with, I don't know, what helps you may be different what helps me. What helps me is to stick with the notation and be really anal about it. So when you're talking about individual electrons, use smaller case stuff. So you'd have little l. How many electrons am I coupling here? 2. So I'll have a little L1, and I'll have a little L2. Okay? So what will be values for my little L's, 1 and 2? Are they both 0?
Mm-hmm.
Yeah. Did we agree with Melissa? Both zeros. Okay. Well, if they're both zeros, see, I made this nice big table for our coupling tables. And we're trying to follow the same format we did when we spent a whole day doing this. What will be my big L's? Anything else? That's it, right? So we're starting out as simple as it can get. Okay, so I'll have a little S's, right? And what will they be? Half. Okay. So my S values for that corresponding L would be what? 1 and 0. Very good. Okay. Whoa. I'm already screwing up my table, right? Remember how we did this? We went down? Okay. So 2S plus 1 for the top row will be?
3.
Kevin, it will be what? 3. Right? Everybody following this? And my J will be what? How'd that Clebsch-Gordon coupling go? L plus S all the way down to L minus S. Pretty much just 1, right? Okay, so for that row, write the term symbols. So it will be the letter. See, I'm talking about writing this guy now.
Capital S.
Capital S. All right. Superscript. 3. Subscript Gloriana. 1. Yeah, I think you're following. Okay. So do the next row. I should have stuck to orange, because then I can use the other next one the other color. So I can use the same table. So what did you come up as a term symbol?
Superscript 1 S 0. Yeah.
Everybody agree? Right? Good. Okay. How about, now again, why would there be 2 states? We just have 1 electron configuration. Why would there be 2 term symbols? Because of?
Spin orbital coupling. Spin orbit.
Yep, spin orbit coupling. Okay. And you're probably only going to see it if you apply a magnetic field. All right. Okay. Derive the term symbols for this electron configuration. Identify the little L's, the little S's. You just kind of fill in the same table if you want. Bless you.
Thank you.
I'll write my term symbols and see if you agree with them. I don't know if I went too fast. Did you get 4 term symbols? Did you get that far? Yeah, I wrote them down too quick. There's only one possibility for L, right? Right? L1 plus L2 down to their difference. Right? Do you agree with that? There can only be one. That's it for L. One, that's it.
That's what I put, but why isn't 0 an option?
Because L1 plus L2 all the way down to L1 minus L2. So 1 plus 0 down to 1 minus 0. So all you have is just 1 for L. Oh, I probably wrote it in the wrong order. Let's put it 0, 1, then it'll match better. Then it matches what I wrote better. Right? Okay, so J is going to go from 2 all the way down to 0 for that one. All right. J here is going to be 2, 1, 0. Here, J is just 1. 2s plus 1. 2s plus 1.
How do you get to 1 0 from J?
J goes from L plus S all the way down to L minus S.
Oh, I see. So, yeah.
Okay, so make sense? Everybody got those?
Test like those all 3 or 4 would be the answer.
Mm-hmm. Yeah, you've got 4 term symbols to work with. Okay? Ready to go on to the next part? Okay, so we're actually going to describe line spectra now. The sodium atom has 2 strong emission lines in the yellow that would not appear if not for spin-orbit coupling. These emission lines are illustrated by the diagram to the right. Okay, so we apply a strong magnetic field and those lines split. Right, the ground state electron configuration for the sodium atom. Now, what I'm going to ask for is the ground state noble gas electron core configuration of the sodium atom. Do you remember that? What was the game for that? What was that? Yes. Do you hear that? You have to give the nearest noble gas in brackets. Right? Is it helium? I don't have a periodic table. I think by this time I'd have it memorized, right?
So, I think it is
Helium? Helium? Okay. Periodic table is a lot easier to look at. Right? We should have one in here. Put over our green chalkboards. Right? And then it should be the very first guy. So 2s1 sounds right. We should look at a periodic table to make sure, though. Where's a periodic table?
Google it.
Google it. Here's a periodic table. Go ahead, you tell me if it's right or not.
Yeah.
Oh, it's neon. That's a 3s1. Okay. Determine the electronic term symbols for the ground state of the sodium atom in the space below. Okay. So is there going to be any, or you have to, page 378 comes into play here. And we talked about it, but we said closed shells have no orbital angular momentum. In other words, the spin paired idea, right? We said in our, and we'd have to go back and find it where we talked about it, but we said that when you have those, there's no orbital angular momentum if the spins are paired up. So that means we can forget about all these electrons here. We don't have to couple them. We only have one electron we're worried about, right? So that's why it's nice to use the noble gas core notation, because it really gets rid of a lot of stuff. So identify your L, identify your S, and they're all smaller case because there's only one electron. But see if you can write the electron configuration of it. I'm sorry, see if you can get the term symbol for it. Make a little table if you want, just like we did before. It's kind of nice to approach every problem the exact same way. That's how I do it. The least amount of stuff to memorize. Identify your L, your S, 2s plus 1, your J's, and then write the term symbols. So what did you end up as a term symbol? Melissa, what did you end up with?
2s.
So the doublet, S half. Great, because that's what they have down here, because they just don't have the doublet written. Right? Good deal. So Alyssa, you got that? Or not?
No, okay, so it's just going based off of the,
Yeah, off of that one electron. So that means L has to be 0, S has to be a half.
Okay.
Right? Everybody agrees? Jeffrey, you agree?
Yes.
Okay. So now let's write the lowest 2 excited state electron configurations for the sodium atom. And I don't think there's any tricks in this case. I think we can pretty much just go straight off the periodic table. Remember, we had a concept preview, and we really should be using it so we don't screw up. It talked about the order in which these heterogenic orbitals were filled up depending on the atomic number. Remember that? But I'm pretty sure we're safe.
Anything greater than 10 use the...
Yeah, something like that. So if we just use the periodic table, what's the, we said 3s1. So if we're going to promote an electron, according to that periodic table, Melissa, we're going to promote it to what?
4. 3.
Man, we should probably, are we over 10?
Yeah, this is 11.
Yeah, we better. Where is that chart?
Scroll up.
Oh, what was that? Oh, here it is. Sodium doesn't look like a trick question, right?
Something about that.
It's not even on the, right? It's not even up here. And you said it's 11? Let's see. So then where so everyone can see it, right? Where's sodium? Sodium is right here. Oh, D. What are you talking about? D's way down here. Not going to be D.
Oh,
What's next? That's what I was thinking. What's going on here? Okay, so it's which P is this? Everyone remember this? 3P. Remember how this goes? This is what S? 1s.
2s, 3s, 4.
Oh, how about this guy?
3d, 4d.
Yeah, I think you remember, right? And this guy is 2P, 3P. Okay, so that's the quick and dirty way of doing it. But when you're over, like Melissa said, when you're over 10, you should probably be careful and use this. But see, sodium's not even listed up there as being funky. So, you know what I'm saying? It's not in here. Over when Z is 10 protons. When the atomic number is over 10, you're supposed to be careful. But we're okay. So if we're going to write the noble gas core electron configuration of the lowest excited state electron configuration for sodium. So our what do you call it? Noble gas core is still neon. And it gets promoted where, that electron? 3p. So you're at 3p with a little superscript? 1. Okay. So that's a possibility. Right? 3p1. We're in here. But it wants another one. So what would it be? Alyssa, what would it be? So now we promoted, we were at the ground state here. Where's sodium go? We're here. So that's 1s, 2s, we're at 3s. Promote it, we're here, 3p. But now we want to promote it again. So you have to go to, where would you go?
If you promote it, would it go up?
Yeah, so the next, kind of think of it as in what order are we filling those hydrogenic orbitals, right? So what's after 3p?
It'd be 4s.
4s, right? That should be the next one. So we'll do the exact same thing, neon, but now we'll write 4s1. So the order in which those hydrogenic orbitals are filled, they call it the Aufbau principle. And right, we can memorize it, but that's too much. We should be able to, use that chart. And when you have to. Otherwise, what we're doing pretty much works all the time. It's just there's some tricks, and that's why we use that chart. Everybody with me so far? Mm-hmm. Okay, so let's go ahead and write the term symbols for configuration 1 and excited state configuration 2. Go ahead and write the term symbols. You can make your little table. Hopefully you get those.
Big S again.
So this is for configuration number 2. And configuration number 2 is this. So that means L has to be 0, right? So that means I'm going to have big S's. That's my only possibility for it.
No, but on the table, how do you get?
Oh, so then this is going to be a half, and then a half times 2 plus 1, 2. This is just going to be a half. Okay, so everybody agree with these? So if you got them, see if you can answer E and F. If you got those answers, see if you can answer E and F. Anybody have an answer for E? You have a 50-50 shot at this. You only have two choices.
Is it the 3P1?
It's the one at the 3P1. Yeah. And you can kind of tell because there they are. And the one that the 4S one only gives rise to one state. So that's not, that can't give rise to multiple lines. That's just one line. So the answer is neon 3P1. And then it says, which transition is forbidden? So it's kind of easy if you see which one's allowed. If you see neon, well, what's the ground state again? Neon 3S1. S1. Okay, that is allowed to go to neon 3P1. That's allowed. What's not allowed? Neon 3S1 is not allowed to go to, yeah,
Energy level?
neon 4S1. Okay, that line, you don't see it. It's not allowed. It's forbidden. So what this is, if you're reading along in the book or following along in the book, this is around page 379 where they start talking about selection rules. And they say that, hey, here's one right here. Delta L cannot be what number?
0.
Can't be 0. Delta L can't be 0. You can't have an S go to an S, a P go to a P, whatever. P going to an S, P going to a D, D going to... You can't have delta L be 0. Oh, they can't go P to P, D to D, that kind of thing. S to S. Sorry. Okay. So that... Now, realize this is atom stuff. Yeah, it's more than one electron, but it's atoms. So we're not talking about molecules. That will be in, I think, chapter 14 coming up. So this is atomic spectra. So now we're on page 2. You have these electronic configurations, and they want you to determine all the possible L and S values. Okay? Ridiculous, right? Now, then once we do that, then we'll be, it's not so bad.
L and S values?
Yep. And then down here, we're going to write the term symbols. Okay. Now realize this isn't that bad because I can cross out what? And not even look at those electrons. 1s2, cross that out. Cross out that because they're spin paired, right? Remember, whose rule is it that when I'm filling in 2p, that I don't do this? Hund. They're both up or down in different ones. That's Hund's rule. All right. So that's all you're doing. It's not so bad.
I really broke it up too. We're not doing the symbol till later, right?
Yeah, we're doing the symbols later. So I don't get you to revolt. So identify what the lowercase quantum numbers of L and S are and couple them.
So for this first one, we have 2 S's.
Yeah. Well, you have a little s,
S1.
little s1's a half. Little s2's a half. Yep. So that means big S would be 1, 0. Little L1 is 1. Little L2 is 1. So that means big L is going to be
1.
What did you say? 2 big L.
2,
And 0.
0, and 1 in between.
Why don't we have 2 L's if it's just 2 P?
Because each electron has
Oh.
its quantum numbers, little l, little s. So all we're really doing here is just prepping to make the big table, right? So we make our term symbols.
Okay, I don't get why we were able to cross these out.
Because they're closed.
Oh,
On
okay.
there's matching orbital angular momenta that are just going to cancel out. Because you have a one in the same orbital, an up and a down.
So whatever orbitals are filled, I can go ahead and cross out.
Exactly.
Okay.
Exactly.
Why did you get, for a little L, why did you get 1 and 1?
Because you have they're both in a P.
Oh.
They're both in a
there's
P.
2 of them. Oh, I
Yep.
see. So on B we can cross out 1 S2 and that's it, right?
Yeah, exactly.
For D, do we have to worry about the 2, 3, 0?
There's no electron there. So there's nothing to couple. A lot of times those things aren't even written, right? They're just there to show you that they're empty. It's promoted.
Are you
just writing it down? Oh, that we're doing the whole chart. Yeah, he just
Oh, you can do the whole chart if you want.
I was about to do the chart and you're like, no.
You can do the whole chart. It's just cleaner if you do all the L's and S's. Then you make nice charts down here. But because you're gonna end up making the whole chart sooner or later. So if you want, go ahead. But
See, I got L and Q and oh, wait,
That's
no,
a
yeah.
J.
God, I'm an idiot. I quit. This one, right? Not 0 also?
Oh, yeah, well, L will equal 1 for the P, and then L will equal 0 for the
No, I'm
S.
talking about 2.
Oh,
Oh, yeah, no.
0, 1, and then S is B.
But for big L, why don't we get 1?
Plus 1 plus 0 is 1. 1 minus
Oh,
0.
yeah, right.
I'm starving too. I haven't even had lunch.
Yeah.
I didn't know that.
Where did you get L? Just big L, just 2? Yeah.